Okay, hello. My name is Dmitiry Kuzьменко. I am a Mind the Bird campaign coordinator, and today is the second webinar about in this series of webinars related to the Firebird 2.5 launch campaign. And I'd like to introduce you and Harrison, the historian of Firebird. I will not tell about the Mind the Bird campaign itself. You've heard about it at the previous presentation. Maybe we will speak about it a bit later. So, Anne, you can start, please.
Okay, let me... Okay, I'm talking about Firebird. Firebird is actually sort of the third incarnation of basically the same database architecture, all designed originally by Jim Starkey. And I am sort of an authority on Jim Starkey because I've been married to him for almost 33 years. And he's standing next to me reading stuff over my shoulder and making me nervous. So we're going to start going way back in history to the point where Jim and I were both working for DAC. This was he started working at DAC in 1976. I joined a little bit later. At this point in time, the big companies in computing were IBM, Burroughs, CDC, the list at the bottom of the slide. Computers were huge and lived in data centers, and you didn't log into them. If you needed something done, you took your request and somebody wrote programs and you got your answers back in a week or so. Databases were rare, huge, and cumbersome. This was after Cod started writing his papers about relational databases, but before there were any even vaguely commercial implementations. At that point, relational wasn't necessarily SQL. SQL is now completely associated. You can't be a relational database unless you're SQL. At that point, there were several other relational languages, including one that Jim had developed at CCA, which was Computer Company of America, which did database work and developed a thing called the data computer. At that point, they were on the ARPANET, which was the predecessor for the Internet. There were 46 computers on it, and that was really exciting. Could you imagine being able to talk to 46 computers on one network? The DEC was just introducing a new model of computing. At this point, it was understood by everybody that relational databases were toys. They might be good for data analysis, but if you wanted performance, you needed a codicil system that lets you specify whether things were stored hashed or linked, and absolutely you needed hard pointers from record to record if you were going to get anything that would perform at all. At the time, Jim was working on a product called DataTree, which, believe it or not, still exists. It was first released, I think, in 1978, maybe 77, and it survived the transition from DEC's transition to being part of Compaq to being part of HP, and it's still available. It's an interactive query language it's a relational language, and the line in the middle is an example of the of what would be a select statement, which is print owner, model of yachts, cross owners, yachts and owners or tables, over model and manufacturer. Those would be the over statement lets you match tables by common field names. And the language was strongly driven by the idea that where in SQL you think of fields as being part of a table, the idea behind this was that the fields were actually domains. They were separate items that were linked together into tables in different ways. So that language, when it came out in 1977, people who were buying it on PDP-11s discovered that they could do their own programming. So they no longer they could type this language, and it had procedures, and you could build up and save larger and larger procedures, and it became a fairly complete small programming environment. And individual departments could manage to buy a PDP-11 and write their own programs, keep their own records, produce their own reports. And after DataTree had been out for a few years, we went down to the Naval Underwater Systems Center, where they were using DataTree, they said, to track whales, but I think the whales were actually Russian submarines. This was a long time ago, and Russia wasn't our friend. And we got a big, we were down there, three of us who worked in DEC's general database area, mostly because they wanted to find out about the directions that databases were going. One of the IT guys there looked and said, looked at Jim and said, "Look, this DataTree stuff is just terrible." So when we do something, when we write a report, we first write a spec, and then we write the documentation, and then we write the code and we test the code, and it takes us about 2 months to produce a report. But it's fully documented, and the code is commented, and somebody comes in here with DataTree and they just knock the thing off in a half an hour, and if they leave, or if we want to change it, what do we do? And Jim said, take another half an hour and do it again. So this was changing the way, moving computers out of a sterile environment and away from IT and into the hands of the people who were using them. And this was a very disruptive thing at the time. And DEC was a really exciting place to be because we were actually changing the world. I think I didn't say at the beginning, and I meant to, that I will check from time to time to see if there are any questions. If there are questions that come up about something specifically that I'm talking about, I'll try and take them in line. Let's see. So you had DataTree, which was this reasonably cool thing, and people were using it more and more, and there was a special interest group for DataTree, and DataTree had its animal mascot. It may have been the first software product with an animal mascot. We were in our late 20s and didn't have much of a life, and we spent a lot of time there. And late one, that's Jim cackling in the background. Late one night, I was sitting around kind of bored, and I started writing. Jim had me writing help text for DataTree, and I decided to do help Wombat, and that drew into help Wombat plus help advanced Wombat. Reasonably correct information. So the Wombat became the symbol for DataTree. We also did a few other funny help texts, like help me, which would tell you, more or less how you. And then there was help advanced me, which just said you were not advanced. And then made us take that out as unprofessional, but they let us keep the Wombat. The problem that DataTree had was that the two data storage mechanism programs, whatever systems that DEC had, were an ISAM, which was single key with no metadata, and unfortunate locking characteristics. And DBMS 11, which was a codicil database ported to the PDP-11, it really didn't fit. PDP-11 was a 16-bit machine with no virtual memory, and trying to put anything big on that, and this was a translation of Cullinane's IDMS. By today's standards, not a big program, but by the standards of that day, really big, and mechanically translated from I've forgotten the language that it was originally written in, into PDP-11 assembler. So it had terrible names for things. I worked on it for several years. It finally got so that it more or less worked, and then PDP-11s and codicil databases all went away at the same time. What DataTree really needed in order to make it easy for people to use and easy for people to maintain and upgrade applications was dynamic metadata, so that you could add fields to tables and add tables without shutting everything down, and it needed multiple access paths. The codicil database, there were fixed access paths from table to table. So Jim worked on DataTree from about 1976 until about 1981, and at that point we'd gone from PDP-11s to VAXs, and the VAX was a big step forward. It was a 32-bit machine with virtual memory, and it just felt as if we had walked out of a box and into the wide open world. At the time of the first VAX release, relational systems had come to everyone's attention at DEC, and they understood that they needed to look at it, but they looked at it more as an academic sort of problem. And they had a bunch of people thinking good thoughts about relational databases, and they weren't at the time. There was almost no independent software industry. Software almost always came from the company that made your hardware, and then so there was no question that we were going to go out, that DEC was just going to say, okay, relational databases, we provide the hardware and the operating system. It was something that they had to grow themselves. And then suddenly Oracle showed up on the horizon, and DEC was convinced that they were losing sales because they didn't have a relational database. And so all of a sudden it went from something that was being studied in a kind of a relaxed, nobody worried if there wasn't much progress mode, to they needed it right away. DEC had written, the group that I was in had written a codicil database for VAX called DBMS 32, and it was a codicil database. It had hard links to stuff and an arcane language for dealing with it. So they decided that since it was well known that relational databases were toys and that they weren't very hard, they just slap a relational front end on DBMS 32 and have it out very quickly. And of course, it took in the end, it took about 3 years. And by the time they were done, there was almost nothing left of DBMS 32 behind the relational front end. But Jim looked at that, and it wasn't going to have dynamic metadata, and it was going to be complicated to access, and it was going to have page level locking. And he said, no, and DEC was reasonably pleased that DataTree was their largest selling software product. So Jim got a year off to go think good thoughts. He thought about a number of things. He did a natural language query language and move that to a speech recognition system, and discovered that at least then speech recognition worked pretty well as long as you had a 10-word vocabulary, but as you got to a larger vocabulary, it started making false hits, and he put in the word turkey to say, okay, kill this. I'm going to start again, and we're going to see if we can get the words right. Unfortunately, it mistook Starkey for turkey one day when he was doing a demo, and he was so annoyed, he pushed the whole thing into a closet, locked the door, and threw out the key. But having played around with a few things, he decided that it was time that he built a relational system that he could play with. And for those of you who've seen the insides of Firebird, you won't be surprised to know that it was called JRD, Jim's Relational Database, at the beginning. And at the time, we were talking about, let me just stop a second. No, nobody's asked me anything. At the time, we were talking in that group about concepts that were going around in data storage in various areas. And one of the concepts was a thing called a shadow. We had 10X, I think, which was a PDP 10 operating system developed outside of DEC, kept shadows of files. So if you were changing a file, somebody could still read the old version. And you know, it was a file level thing, but we got talking about, you know, couldn't that be used to provide a stable snapshot cheaply, so that read-only programs could run kind of behind updates and provide better concurrency. That idea had been kicking around. We've been talking about it a lot. The other thing was that I believe it was in the second version of VMS, they introduced a thing called a VAX cluster. VAX cluster is a shared disk, separate memory cluster with an arbitrary number of machines all talking to a single disk system. And access to the disk was controlled with a distributed lock manager. That was the new hot thing. There had been a PDP 11 version of it that never went very far, but VAX clusters were so this database needed to be able to run on a VAX cluster. That was becoming a problem, well, for all of the databases. When you're just doing access to files, it's not so hard. But when you're doing, because you have relatively few locks, even if you're doing page locking and you're planning on high concurrency, which reminds me, and here's another small offshoot. When I was working on the PDP 11 database, somebody from another part of DEC came over and explained that she absolutely needed to put 100 clients on this PDP 11 database, and could we handle that? And I had to point out to her that you really couldn't make more than about 20 connections to a PDP 11 in any case. They couldn't run more than about 20 users, so it really wasn't likely that we were going to support 100. But this is the level of, so going to a VAX cluster meant that you actually could possibly imagine having 100 users on a database all at once. And that would mean lots and lots of locks. The lock manager ran at, oh God, I've forgotten the name from DEC, but it's a kernel level. And it used physical memory, and there was an absolute limit to the number of locks that you could maintain, and it was fairly obvious that the next round of databases had to lock at the record level rather than the page level. And so talking about shadows, talking about fax clusters, and how many locks. One day as we were driving down the highway, Jim suddenly said, I've got it, and came up with the idea that became MVCC. And I'm going to take which is multiple version concurrency control. The idea was that you could use multiple versions not just to provide a stable snapshot for a read-only transaction, but also to control interactions between writers. And I'm going to back up here and add another small note, which is one of the things about JRD that's different from most databases today, although it wasn't particularly different at that time, is that it was a single file database. Most other implementations were either one file per table with the indexes or separate files for tables and indexes. There were a couple of reasons why, and they came from the DEC culture, why it was a single file. There was a substantial cost to doing a file open. There were a limited number of files that you could have open. And we had, at that point, the vision that storage was a separate area. It was a separate problem. DEC's storage group, we built DEC built disks too, was a group in Colorado, and they were doing striping and shadowing, and the software database people there at DEC were very strongly of the opinion that the disk people could take care of disk accesses, and we didn't need to get deeply into things like placement control and, to make the databases work. We could count on the storage people doing their job. It was about this time that the Britton-Lee machine, which was a relational database machine, was developed. And the Britton-Lee people came into DEC hoping to sell DEC, the DEC would sell their machines. The first machine didn't have any way of doing a software upgrade, and they were asked, and they said, no, we'll never have to do a software upgrade. We'll test it very thoroughly, and it'll be perfect the first time. They didn't go very far either. So we had this idea, and Jim's databases fairly consistently have that storage is the location of bits on the disk is somebody else's problem. The other problem, what the Britton-Lee machine did is inspire DEC to try and build its own database machine, and they worked on developing hardware that would do sorts quickly, looked for database problems that could be resolved in hardware. And the problem was that by the time they developed a piece of hardware, general computing hardware had gotten sufficiently faster that at no point was the specialized hardware faster than a general machine. And that made a big impression on those of us who were there at the time. It wasn't worth trying to build special equipment to make parts of the database faster. The hardware, generic hardware worked, came along faster. Anyway, going back to MVCC, because that turns out to be the major aspect that it's part of all of the databases that Jim has done. Since then, Postgres uses it, a number of other. So back in the early 80s, it was well understood that the way you handled concurrency in a database was with record locking. And I have this mental image of little tiny locks that actually sit on records on disk, but of course that's not the way it's done. You have bits that say that something in a lock table that says that things are either free or or locked. And the record locking protocols, the lowest level, and this was the level that I think I know DBMS 11 did on the page level, was just hold write locks. If you have changed a page in a transaction, you don't allow anyone else. You put an exclusive lock on it. Nobody else can read or write that record. And what that eliminates is dirty reads and dirty writes. You don't have somebody overwriting a change that a concurrent transaction made, and you don't have any chance of seeing a record that was changed by a running transaction. And then, and the second level is holding read locks on records. In that mode, you get your read is repeatable, except that you also see records that were created by transactions that hadn't committed when you started, but had committed while you're going along. So if you count the number of customers once in a transaction, you may get 15, and you count the next time and there are 17. You'll only see more. Nothing will ever go away. The third level rather is to hold predicate locks, and that gives you a consistent read, meaning that you will never see. If you see 15 customers, nobody's going to be able to store a 16th customer. And it also makes the transaction serializable. And at this time, which was the early 80s, it was generally considered that because in a locking protocol, because everybody looked at things from the point of view of locks, a consistent read and serializable were the same thing. And MVCC provides a consistent read but is not serializable. I know most people writing applications today manage to live with, if they can live with MySQL and no transactions, most people seem to be able to write applications that are reliable without going to serialize to a consistent or to a serializable level for sure, because the implementations, a predicate lock is a way of describing it. Predicate meaning that if I say I want to see customers in California, you could think of it as I'm locking the concept of customers in California, and no one is going to be able to alter customers to be outside of California or alter customers from someplace else to be in California. But in fact, they're implemented by locking in the systems that I know of, by locking the access path to a branch to a group of records. That is, if you're looking for customers in California, it will lock the index, the part of the index that covers California, if your state is indexed. If it's not, then it just locks the whole table. Essentially, as the the primary relational database project went along, they discovered that they were getting huge numbers of deadlocks and using huge numbers of locks. And had to come up with strategies for you would start by locking the whole table, and then if somebody else wanted to use the table, you'd back off your lock to pages. If somebody wanted to share a page, you'd back off to records. And then if the total number of locks went too high, you would go back to locking pages and just reduce the granularity of the concurrency in the product. And this also meant that they were pushing huge numbers of locks through the lock manager. So Jim had looked at all of that and said, no, we really need to find another way of handling concurrency that doesn't involve so much low-level traffic and so many opportunities for applications to lock each other out of the data. It is generally understood in the world that MVCC was invented by David Patrick Reed in his thesis called Naming and Synchronization in a Decentralized Computer System, which he wrote at MIT. And he does use, it is a system that uses shadow records and provides a consistent view of data and tracks the records with what he calls a pseudo timestamp. And it's superficially very similar. However, his system uses optimistic locking, and here it's another long aside. There are two other ways of looking at concurrency control. One is that you assume that everything is going to go right. You make all of your changes wherever you want, and at the end, you check and make sure that there weren't, in fact, any conflicts with concurrent transactions. And that's the system that that Mr. Reed's thesis used. And it also used timeouts. The difference in MVCC, the way Firebird uses it, the way InterBase uses it, is that if you try to update a record and you can't see the most recent version, you stop there and either get an immediate error or wait until the transaction that made the change finishes. This optimistic concurrency control is probably good in some cases, but it leads to in situations where there really is significant amount of conflict, it leads to having to undo and redo a lot of work. And having a way of using shadows to produce a system that has pessimistic concurrency control, where it's assumed that if there is the appearance of a conflict, that it is a conflict, and that it will, and that you should not proceed with what you're doing. So that's the idea that really was the essential difference, and we were completely unable to convince DEC, Jim was completely, that it actually worked. It could be demonstrated that it worked, but so they had two concurrent database projects, and this is a slide from one of Jim's more recent presentations. As I had said earlier, lots of people assumed that if you were going to see a consistent view of data, that is, every time you did a select on with the same qualifiers, you got the same data. The only way to do that was to do the 3 levels of locking: write locks, read locks, and predicate locks. And since that also produces serializability, there was an assumption in that serializability was essential for making transactions really consistent. The acid properties, atomic is pretty easy, pretty clear. You know, it happens or it doesn't happen. The whole transaction runs, and then you never see part of a transaction. It succeeds or fails as a unit. Isolated is also fairly clear. You don't see the work of other transactions. It's interesting that the places where an MVCC system is not serializable actually happen because the transactions are so isolated. And I should have probably put in a slide here showing where it is not serializable, but maybe you can imagine it. Suppose you have a table with one field, which is an integer, and you have a single transaction type, which is to count the number of records in the table and store that number into the table. In a serializable system, you would obviously, there'd be a record of 0, 1, 2, 3, 4, up to however many transactions had run. In a MVCC system, you could easily have 0, 0, 0, 4, 5, etc., because concurrent transactions don't see each other's results in a select. So there would be 3 or 4 separate transactions that would see 0 and store 0. And that's not a critical, I mean, obviously if you care about getting things serialized, you put a constraint that says that those numbers have to be unique. The durable property, also well understood, has to be on oxide, or at least on oxide before the transaction commits. Consistent is, you see different definitions of consistent, and the one that makes sense to me is that you get a view of the data that is consistent, so that within your transaction you're working as if it all happened at the same instant, and you see the database just in a single state. And I think there is a good argument that serializability, the confusion between serializability and consistency, is the result of everybody's looking at database concurrency control from the point of view of locks rather than in any abstract way. JRD had some other innovations, and it has taken a long time to sort of isolate which things are integral. One of the things that seemed to be integral with having record shadows was using the database as its own log. And it turns out that those ideas are separate. At the time, most databases had 2 logs. When you wrote a change, you wrote it to the log. When you committed, the log was applied to the database. And it also had an undo log, a list of things that needed to be undone. So you really were writing in every piece of data went into 3 places. And in JRD, the shadow records provided their own log. While your transaction wasn't committed, your change was present, but no one could see it. And if your transaction failed, someone sooner or later would come along and garbage collect the record versions that you'd created. That's somewhat related to our using, I'm sorry, our idea that storage was a separate place, and we didn't worry particularly about disks, because it turns out that an advantage of a write-ahead log, as opposed to writing directly into the database, is that the log can be doesn't require random writes, so you have less latency in a commit if you have a log. I'd started out earlier saying that dynamic metadata was one of the absolute requirements that Jim had to support data creep, and we also had a view at that time that most applications were going to be done through fourth-generation languages. And that no one would program directly in SQL. There would, or our data language or anything else. That there would be these fourth-generation languages that hid some of the complexity of actually talking to a database. Blobs. It was a new data type, large unstructured thing, actually named after a movie which I think is The Blob That Ate Cleveland. After we had left DEC and gone and sold. What was that term? Anyway, at some point, blobs went into the DEC databases. It was felt that the word blob was unprofessional, so they got called segmented strings. And some years later, when InterBase was out, one of the DEC product managers decided that there was a critical need for blobs, and made an announcement that DEC would have blobs in the next release, not realizing that they'd had them there the whole time. And another thing that JRD did that's carried through to Firebird is two-stage index lookup. Rather than, when doing an index lookup, many systems go look at the index, use the index to go find a record, return the record, go to the index, find the next record. Firebird and JRD and Netrostructure all look first at the index and set bits representing the records that meet the criteria, the indexed criteria, and then they go back and read the records in storage order rather than reading them in index order. This is bad if you're using an index to sort. It's very good generally because you get all of the records off a single page in one retrieval. This is probably less important now that caches are huge. I mean, we were talking at this time. DEC couldn't afford to give any database project access to a gigabyte. We used to talk about, wouldn't it be neat to see what happens if we actually had a gigabyte of storage and see where our algorithms break down. So this two-stage index lookup has an advantage of reading records in storage order, and so the read retrieval is faster. It also means that you can use multiple indexes. It turns out there are some subtleties there that took decades to fix. Like if you have a very selective index and a very non-selective index, it's probably a bad idea to use them both. But if you have two semi-selective indexes and you and together the bitmap results, you get the effect of a compound index, and that you can use even with if all of the terms are not equality. Let's see. Questions? Nope. I've missed. Okay.
I'm starting to post questions. I can speak it. Some people from other databases like Oracle and Informix and so on, who works with them now, tells that Firebird's drawback is not having the transaction log. From my point of view, database as a log is good, but they maybe.
Okay. Yeah. I know.
Maybe this question is just a rhetoric. So.
In Falcon, which was the version of the net receptor database that Jim did at MySQL, we did go with a log just because it reduced the commit latency. And I know, I think it's Tom Lane from Postgres who says, well, you know, the reason that Firebird databases get corrupt is that there's no log. And I think that it simplifies things, and not having a log. It does make the database programming more difficult, because it requires that we use a careful write strategy, and that's a delicate mechanism, and if you've got some ham-handed programmer coming in not thinking about things, you end up with situations where a crash can leave the database inconsistent. But in fact, Firebird is very crash resistant. So, yeah. And there are certainly people who say that the two-stage index lookup is a problem, and we have to implement each of the databases has a second, maybe navigational method of index access that does walk record to record, and that supports the first, select first n, because people have learned to use first or limit or whatever syntax their database happens to use for that, to say, well, I don't need to have fields that qualify the kinds of records that I'm looking at. I'll just ask for everything sorted, and I'll take the first 10, and man, is it expensive to get the first 10 if you've already sorted a million records before you return those next 10. So Firebird has two mechanisms, and the optimizer recognizes cases where it can use a navigational index to optimize queries with the first. Okay, at this point, I'm way over the time that I expected. So a little bit more history. We had at DEC this year and a half of what we called the Database Wars, which was a play on the Clone Wars from Star Wars. There were two projects. They had two radically different implementations. At this point, Jim's project was supported by disk engineering as being the basis for a database machine, and DEC had begun its death spiral at this point. And when you have a company that's growing and you have a manager who isn't that terrific, you put him off in an area where he's not going to do much damage. When you've got a company that's shrinking, all of the good people rapidly go away, and you suddenly get this massive number of really bad managers, and that was, people were unwilling to make any decision. So they let the two projects go on, but they insisted that the two of them have a common API, common system tables, common error codes, so that you could change databases just by your program would run against what was by then called RDB-Elan, a JRD database, or a RDB VMS database just by changing a shared library. What this meant was that the program API had to be worked out in excruciating detail and was fought back and forth by the two groups. We had yeah, right, Jim's laughing in the buckets of blood. We had, they hired an architect to drive this process of coming up with the common interfaces. He had a PhD in philosophy from Heidelberg and a degree from Carnegie Mellon, and he was a short, heavy-set guy who, when he was at CMU, worked as a bouncer at a bar called the Buckets of Blood outside the steel mill in Pittsburgh. And it was intimidating having somebody there who could probably pick you up with one hand and squash you. And it made us behave rather better than we had been. But that process is the reason, I think, that Firebird and InterBase have managed to survive, because the basic API was really thoroughly thought out at the time. Yes, there have been changes in access since then. Anyway, so at this point, the 7 computer companies that I had listed on the first, or on the early slide, were mostly gone, and now suddenly the big players were DEC, DG, SGI, and Mini Computers, and it was time for another revolution. After what eventually happened was that DEC decided that they would release both databases, one as the official VMS database and one as a database for an embedded computer system called Elan. But it wasn't fun anymore. So one day, Jim was cross-country skiing, I think. It occurred to him that for a wedding recently, he had to get a gray pinstripe suit. And if he had a gray pinstripe suit, he could start his own company. And so he did. Started it in our spare bedroom. Got an agreement from Apollo Computer, which was part of the new disruptive computer systems, workstations. Up until then, everything had been time sharing. Now you had a network of separate computers that talked to each other, so we had built the house that we were living in with the idea of putting in with Ethernet. It turned out that Apollo needed a different kind of cabling. Every time I built something in, it turns out to be the old technology. So Apollo funded the original development with the idea that they were going to have a private label database, because at the time most software was still private labeled by the manufacturer of the computers. And we picked up a guy who did some marketing and some writing, and generally was, and so there were 3 of us working from home, and suddenly we needed what had been our guest room needed to be the copy center, and the dining room was our corporate lunchroom, and my kitchen was filling up with other people's mugs and food. And then one day I got up and discovered that my bathroom had been turned into the coffee room, and we moved out of the house fairly soon thereafter. It is really nice not to have other people working in my house. Groton Database Systems was the name we adopted. We were living in a town called Groton. Our marketing / documentation guy used to answer the phone, Rotten Database Systems, and we needed another name. But we'd gone through, I guess, several $100s in legal bills trying to find a name that our lawyer would approve. Eventually, we decided we were going to call ourselves InterBase. The lawyer said that name is already in use, and we said, oh, we don't care. At the time, the relational language that we used was what's now called, what we call GDML. It was based on the language of the data tree and the data computer. Our philosophy was that SQL existed. We would live with it, but any innovations that we did would be in GDML and not in SQL, because the purpose of SQL was to let people migrate programs to us, and if our SQL wasn't like other SQLs, it wouldn't work. And we expected that people would write two kinds of programs, programs that could be pre-processed, and they would put our GDML language directly into the program. And then anyone who wanted to do dynamic work with it, where you were building statements on the fly, would probably be using a fourth-generation language, which would hook into the database at the API level. That never happens, and we built a DSQL that sat on the client side and talked the API to the server. That turned out to be really expensive in terms of shipping metadata out to the client. Then we come to, we've renamed ourselves InterBase. We've moved from our house into office space over at dry cleaners, and we had lots of stories there. At this point, InterBase's first version had triggers but not stored procedures, and stored procedures had a kind of a dirty name. The reason we didn't do stored procedures was that Sybase had stored procedures because their cost of optimizing, parsing and optimizing was so high. And it wasn't until after Borland bought InterBase that it got stored procedures, and suddenly it dawned on Jim in particular that stored procedures were not about reducing the cost of executing, but about modularizing and pieces of code. Jim says in the background, Jim blew it. At the time we were in Kingsborough, Apollo was also changing. They decided that they needed Oracle. Oracle wasn't willing to port to their somewhat odd system unless if they had a private label database. InterBase was in field test at Boeing, Lockheed, a bunch of big engineering places. Apollo built engineering workstations, and we were able, when Apollo said that it wasn't going to release the private label, they transferred all of the beta customers to us, and we succeeded in keeping almost all of them. There were some, it was for these engineering efforts that we added arrays. Arrays are were only in GDML, and we never put in SQL support for them because it was an extension. And at the same time, there were user-defined functions because there were, as you know, a gazillion different functions, and some of them with multiple definitions. The sad part of arrays was that we put them in, I think it was for Boeing, and the group that we were working with just loved them. But their IT group said they couldn't use them because they were non-standard. We spent a lot of time fighting IT groups who were absolutely convinced. I mean, they would have an evaluation, we would win the evaluation, and they would say, oh, the evaluation was flawed because the wrong person won. It was really felt like pushing a rock uphill. And I'm going to skip the owning a programmer's soul story. If anybody wants to hear it, I'll tell it later. So we were in a cycle where we didn't have quite enough money to do marketing. Without marketing, we weren't getting sales, and without sales, we weren't getting money. So we went looking for investment, and Ashton Tate was at that time. There were three big software companies: Ashton Tate, Microsoft, and Lotus. And Ashton Tate made an investment which allowed us to move away from the dry cleaners, which was a good thing, and into real office space. And the agreement was that they would make a small investment, then they would make a larger investment and take over 50% of the company. And at the same time, we would develop our InterBase to be a back end for, I think it was going to be DBase 4, maybe DBase 5, port to OS2, and we spent a lot of time becoming word-for-word compatible with Ashton Tate. Ashton Tate was an investor for about 5 years, and when we started, we were delighted to have their investment because not only did it give us money, it also gave us plausibility. And by the time 5 years later, they were in serious collapse, and they were saying, well, we're great because we've got InterBase, which is this real database. It was a peculiar time. Ashton Tate, even when they bought the whole of InterBase, recognized that InterBase was not something that they didn't understand. Their idea of selling software was to put it in brightly colored boxes and put it on shelves, and people would buy it. Our model, we had salesmen, they made calls, they got RFPs, we did projects to demonstrate that we could support them. We had probably a 6-month sales cycle. Ashton Tate had enough sense to recognize that that was something they knew nothing about, and they just left the company alone. But then Ashton Tate collapsed, and Borland took over, and like most companies on the rise, they were convinced that they knew absolutely everything and there was no problem they couldn't solve. So they moved the company to California and left probably 3/4 of the employees behind. I think they took 3 engineers. And moved, did a port to Windows. Up until that time, we've been running on networks of workstations, which were really peer-to-peer computers. There might be one that was the server that held the disk that had the database, but it was only on the Windows port where we picked up Super Server. DSQL was moved from the client to the server, so that the whole DSQL API came after the Borland acquisition, and they also were the ones who implemented stored procedures and abandoned GDML without picking up, integrating the features that were GDML only into SQL. And then InterBase continued at Borland until 1999 or thereabouts, in 1999, when the dot-com boom was in full scale. And at that point, companies were evaluated on their growth. Borland looked at InterBase and said, different area, marginally profitable, not growing. We don't have any use for it. And they got rid of all of the management. At that point, I got back involved with Firebird. I've been somewhat involved with Firebird, with InterBase. I've been somewhat involved with a support list. And after when the customers explained back to Borland's management that no, killing InterBase was not going to work, it occurred to them that what they could do is spin it off as an open source company, retaining a significant ownership, and maybe as an open source company it would boom with the rest of the .com stuff. And since there were no managers, I stepped in. The InterBase engineers had been doing a weekly meeting with the president of Borland, who was the next person up the hierarchy from them. So I stepped in. We started negotiating to build a separate company, and then in early 2000, the .com bust came, and suddenly a part of the company that was, not growing very fast, but was actually making money, became an economic factor, and we had a really exciting WorkOn, the Borland conference, in July of 2000, where we went out to announce the new release, the version 6 of InterBase, and the open source InterBase company, and it got canceled in the opening remarks of the conference. So they did open source InterBase 6 without test system or documentation or anything else. And those of us who had been working on getting the open source InterBase going picked ourselves up off the floor, and that was how Firebird came about. And basically what I wanted to say was that there is a lot of innovation in Firebird, and it's an amazingly long-lived architecture.
Thank you. Great. May I ask my questions?
Sure.
Yeah. So I need to say that anyone can ask questions in the Q&A menu. So and why people doing this? I want to ask my questions first. So the first question is, what was the hardest thing in implementing the RDBMS engine?
What was the hardest thing? Interprocess communication, particularly in the early years when there were, we were running on about a dozen different platforms, and each of them had its own model for interprocess communication, and several of them didn't work very well. So
Yes, okay, I understand, because I know that since then FreeBSD have some problems with the super server.
Yep. And one version of Apollo added a new, I've forgotten what they called it, but a new way of signaling between processes, and it turned out that under load it would drop messages, and that required a complete rewrite of the lock manager for Apollo after we figured out that there was a problem and that they didn't know how to fix it. So.
Well, next question. Was the code that needed to be rewritten completely, and how many times that happened? I mean, for example, from scratch. So you understand that this code needs to be rewritten and throw it away.
Not that I can think of at the moment. I mean, obviously, between RDBLN, which was written in DEX language in Bliss and was DEX copyright, the whole thing was rewritten from scratch in C. I think you would still find pieces of InterBase version 1 in the current Firebird, in almost, not in the new modules, of course, but in the old code with the lowercase 3-letter names. There's, yeah, I don't think, I can't think of anything that we just looked at and said, no, this doesn't work at all, and it needs to be rewritten.
Thank you. Next question. How many time went from ideas to the first release?
Let's see. I think the InterBase version was about a year from
the shower.
From the not from the shower, but at that point he from the moment that Jim said, okay, I'm going to do it, and started sitting down to type it in, was until we had customers running, was about a year. I'm trying to remember whether it was about, it may have been just about a year to beta, and another 6 months to release. The JRD was closer to 3 years and never really got released at DEC. There were people running it. So is that? And the second release of InterBase took about 3 years. Part of that was that we needed to rewrite the interprocess communication for Apollo after we'd gone to beta. And the more people we added to the company, the longer the releases took.
Okay. And can you answer the question in Q&A, because I'd like to leave my final question as final.
Okay. Are there, I don't, okay, let me see, yeah. Okay. So the question is, can I please comment on recent implementations of MVCC MS SQL and so on. In past years, many gurus stated that optimistic locking is not for serious project. Now things seem to be changed. Do you think it is the finished battle between optimistic and pessimistic locking? First, I don't consider what Firebird does to be optimistic locking because it does stop. It does stop on write-write conflicts. It doesn't. You don't run a transaction to completion and then go back and look for problems. However, let's see. I don't know the MVCC's implementation in MS SQL particularly. I do know that there are implementations. I think Oracle has one, and I know that InnoDB in MySQL uses it. They use a combination of snapshots for read and locks for write, and that produces a really bizarre concurrency, which is actually what happens is that if you do a select for update, you get one value. If you do a straight select, you get another value, because your select for update is based on locks and reads the most current version, most current committed version. And I don't know where things are going. I think Jim's current project is also based on MVCC, but uses it in a much more prominent way. It's an essential. In the case of the single processor databases, you can get by with a locking system, and people have got to be smarter and smarter about making cheap locks. So record locking is a plausible solution, but it is not a plausible solution if you're building a cloud database. And yeah, there's going to be a big fight about that, assuming that Nimbus gets its place on the stage. Okay, how about further plans involving Firebird? I expect to continue. For me, the project has its own plans. I am not a developer on the project. I've been away from it for 6 years. I do follow the architecture list and put in my comments, but I'm not a developer. So the project, my plans are to continue doing what I've been doing for the past several years, which is to say answering support questions, filling people in on the history of why things were done, and generally being a gadfly.
So I think yes. I think I can add. I can ask my final question. Or another one.
Mm-hmm.
So please answer from Q&A.
Okay. I'm sorry. I have somewhat. What wrong directions and other negative moments you can call in current Firebird development, maybe moving away from a small smarts to a large and unwieldy, and what Jim is talking about it. Jim doesn't talk about it very much. The Vulkan experience was not great. Firebird's major weakness now is its performance on multiprocessors. 2.5 makes progress toward fixing that. There are lots of ways of doing development and lots of ways of moving projects forward, and you have to pick a path that works with the engineering group that you've got. I think that the current project is moving incrementally toward a model that works well on multiprocessors, and I think that's a good thing. What I would like to see more emphasis placed on is there sometimes seems to be a debate about whether dynamic metadata is a good thing or not, and there are obviously people who think that you should never change metadata without taking the system offline. I think that most applications are now really have to be available all the time, and taking a system offline to do metadata changes is a problem. It requires even more care than careful right to make sure that that a change is not disruptive and that it gets propagated properly. And that's really, if I were thinking about what I would like to see the project pay more attention to, it would be keeping metadata updates dynamic and concurrent. It's an easy cop-out to say, no, just always take the database offline and make your changes and then bring it back up. I think the structure is still in the project for that would allow fully concurrent metadata changes. So that's my thought.
Thank you, and I really define my last question, and it will be last, I hope, because we're too late. So the question is, what do you know? What is real or unreal about things like Abrams M1 reboot shot, soldiers with Unix backpacks, and so on? Have you heard anything about
like that? This? Yes. The early history have you seen the picture? Yes, I've heard about Abrams tanks and the fact that it did not have a recovery process. That's, I mean, should have mentioned when I was talking about logs is that because InterBase is its own log, when after a crash it comes back immediately. InnoDB, for example, the MySQL transactional engine, can take hours to recover after a crash. And so the story is that the Army used InterBase in places where, like the Abrams tank, where they had lots of disk crashes because it was just a very, very rough environment. We had some very peculiar customers at InterBase in the early days after we left, after Apollo. Among others was the U.S. Army Food Service. We also, I mean, we were scraping after Apollo decided that they were not going to fund the whole thing. We were scraping along, trying to figure out how we were going to pay people enough so that they were able to pay their mortgages. And somebody showed up out of the blue and said, well, gee, we really like InterBase, but you've only got a preprocessor for C, and we would like to have preprocessors for Pascal and COBOL and, I don't know, 3 other basic, and I have no idea. And they paid us $100,000 to do that, and that got us through a tight time and to the point where we had some more customers and things were okay. That was just, to revert to Latin, it was a deus ex machina, this miracle that came out of the sky. And Jim still thinks, and he may be right, that there was somebody somewhere in probably the military that wanted to see this thing succeed, if not succeed, at least not die. So we certainly never had anybody come to us and say, we've got a database in a tank that's busted, could you come fix it? On the other hand, it may very well, it may be true.
A friend of mine at 97 made a picture. He took Abrams M1 picture somewhere and put a writing on it in Photoshop. InterBase is inside or something, or powered by InterBase. So it was. So I was trying to find this picture, but it's somewhere.
We did have some open military and in particular spy agency customers. The first head of our users group was in fact an officer with the NSA. He couldn't tell us what he did, but a funny guy. They got a per diem when they were traveling, and he spent the per diem on beer, and stayed in a trailer that leaked when he came to visit us or came to a conference. So yeah, there's, who knows.
So thank you. No more questions. I think it will be one of the greatest recordings in this year.
Well,
so
thank you very much.
Thanks all.
Okay, bye.
Goodbye.